On this worksheet, we're going to be doing two examples of using reaction mechanisms to determine the overall rate law for a reaction. We have, for the first example, we have this mechanism right here. These are the two elementary steps of the mechanism. I'm going to label them step 1 and step 2. And the first problem is asking us to compare K1 to K2. So right here in the problem, this is telling us that the value of K1 is much smaller than the value of K2. So K2 is large. And this gives us information about the relative rates of the reaction. A small K value, a small rate constant, means that the elementary step is slow, and a large rate constant means that the elementary step is fast. So our slow step in this mechanism is step 1, because step 1 has the small rate constant, which means it moves more slowly. Next thing that we need to do is write an equation for the overall reactions. To do that, we're just going to be combining the two elementary steps by just simply adding them together the way that we've done with previous material. So when we add them together, these are all 4 of our reactants. We have NO2 and O2 or O3 in step 1, and we have NO3. And then we have a second NO2 molecule. So I've just taken these two and put them together with the coefficient of 2. And then for our products side, we have these 3 molecules, NO3, O2, and N2O5. And then just like we would normally do whenever we're combining 2 equations together to make an overall equation, we want to simplify the equation by canceling anything out that appears on both sides. So it looks like NO3 appears on both sides, so we'll just go ahead and cancel that out. Anything that appears on both sides is an intermediate. That's going to come up later on this worksheet, but I'm just going to go ahead and label it right now. So anything that gets canceled out from this overall equation. So now it's asking us to write an individual rate law for the first step. To do this, so if we're writing rate laws for each individual step, we want to use the term rate. We want to use subscripts. So for example, instead of just saying rate, we'll say rate sub 1 to indicate that it's for step 1. And we're also going to do the same thing for our rate constant. So we're going to say K sub 1 instead of K. And this again is to indicate that it is for the first step of the reaction, or step 1 of the reaction. Rate laws are where we take the concentrations of our reactants and we raise them to some exponent. So we have NO2 and we have O3. The reactants for step 1. Now, one thing that is unique about using elementary steps to write rate laws, for an elementary step, the stoichiometry of the reaction is going to be the same as the exponent in the rate law. And this is only true for elementary steps. So in previous examples where we've had to put an x and a y in here and solve for the value of x and y, in those situations we were writing rate laws for an overall reaction, not for an elementary step. So this is the rate law for step number 1, and then we're going to do the same thing for step number 2. So this is since this is elementary step 2, we're going to say rate sub 2, and we're going to say K sub 2, and then we're going to go back up to that equation and find those reactants, NO3 and NO2. NO3 and NO2. Question number 5 is asking us to list the intermediates, and remember we labeled that when we wrote the overall reaction. The intermediate for this is NO3, and again, an intermediate is anything that is not a product or a reactant, but still present in the elementary steps. So the intermediates are going to be things that you will see in the elementary steps, but not in the overall reaction. In the overall reaction, that NO3 term disappears. So that's exactly what we're looking for. We're looking for a molecule that we can find in an elementary step, but we can't find in the overall reaction. Not a product or a reactant, but it is present in the elementary steps. Now, one of the challenges with the intermediates, especially if they're appearing in our rate laws, since they're intermediates, they're not products, they're not reactants, they're not things that we can measure in a reaction. So if we have a rate law that includes an intermediate as one of its terms, it makes it impossible for us to actually use this rate law the way that it's written. Again, that's because intermediates are not measurable entities in a chemical reaction. They're not made, they're not produced, they're not used. Okay, so we're going to write an overall rate law for the reaction. Now, the overall rate law is going to be dictated by the rate law of the slow step. That's super important, and that should make sense to you. The slow step is the one that's controlling the overall rate of the reaction. So what we have to do is go back to that previous page. We need to find, remember which step is the slow step, and then we need to find the rate law that we wrote for that particular slow step. So let's go do that. We said slow step was step 1. And that means, here's our rate law for step 1. This is the rate law that's going to dictate the overall kinetics of the reaction. So I'm just copying it right here. That's what we had. Because we are wanting to write this in terms of the overall reaction, this form of it is specific to elementary step 1 because of these subscripts 1 and 1. So we're going to rewrite the rate law of the slow step using just rate and just K. I'm going to do that in a different color. Rate equals K NO2 O3. And we want to make sure that none of the molecules that are used in this rate law are intermediates, because again, we can't measure our intermediates. They're not reactants, they're not products. Our intermediate was NO3, and this overall rate law has NO2 and O3. So that means that this overall rate law is good. This is accurate. So the last thing that we're going to do is compare the overall rate law that we wrote here. So I'm going to just kind of copy that. We want to compare this rate law to the individual rate laws. So I'm going to paste those over here. I'm actually going to move this one right there. We want our individual rate law number 1, and we're also going to look at individual rate law number 2. And when we're doing this, what we're trying to do is come up with an expression for the rate constant K in the overall rate law. So we're looking at the overall rate law. We're trying to come up with an expression for K, the rate constant, in terms of our individual rate constants, K1 or K2, or maybe both K1 and K2. So this is where we kind of have to finesse a little bit. In order to do this, we're going to look at this rate law. We're going to compare it first to this rate law. We're also going to look at this rate law and compare it to this rate law, and we're looking for similarity. Now, you might be saying, I think I might be missing something here. This rate law is identical to this rate law, and sometimes that happens, and it's kind of lucky when it happens. The only thing that's different between these two that I've highlighted is that we're using the term sub 1 in the blue, and we're not using that sub 1 term in the one that's in pink. But other than that, these two are perfectly identical. And when something like that happens, we say, yes, that makes this really easy. If this is my overall rate law, and this here is an individual rate law that matches it almost perfectly, from that, I can say that my overall rate constant K must be exactly equal to K sub 1, because otherwise, everything is exactly the same in these two reactions. So this is our expression for the term of the rate constant K. It only involves K sub 1. It doesn't involve K sub 2. This is kind of like an abstract, weird concept, but thankfully we have a second example that we'll be able to use to practice this again. So moving on to example number 2, this is our second reaction mechanism that we're going to use. First thing that we're going to do is just begin right away by writing a balanced equation for the overall reaction. So we're going to combine these two equations together. Starting with our reactants I'm going to label these step 1, step 2. Step 1, we have H2, we have 2NO, we have a second H2, and we have N2O. And then our products in step 1, we have N2O, we have H2O, we have N2, and we have a second H2O. So there's our overall. Now we're going to write a rate law for the first step in the forward direction. Because this is in equilibrium, we can write a rate law for the reaction proceeding left to right. We can also write a rate law for the reaction proceeding right to left. So for the forward reaction, like we did in the previous example, we're going to use rate sub 1, indicating that it's step 1. We're going to use K sub 1, again, indicating that it is step 1. And then our reactants, H2, and NO, and that NO is going to be squared. Remember that in an elementary step, the stoichiometry is the same as the exponents in the rate law. Now we're going to do the same thing, write another rate law for the first step in the reverse direction. Because this is in equilibrium, it can also go in the reverse direction. Because this is still step 1, we're still going to call this sub 1, but to indicate that it's moving backwards, we're going to say -1. So rate sub -1 means that it's step 1 going in the reverse direction. And then that means our rate constant, we're going to call that sub -1. Again, it's the first reaction moving in the backwards direction. If we're talking about the reaction going from right to left, then our reactants are the things that are on the right-hand side of the arrow, N2O and H2O. And we'll always do this every time we have an elementary step that exists in equilibrium. We'll write 2 rate laws, one for the forward and one for the reverse. Now we can do step 2, write an individual rate law for step number 2. So this is going to be rate sub 2, and it's going to be K sub 2, and we want to find our reactants for step 2. Step 2 doesn't exist in equilibrium, only in the forward direction, so this is going to be H2 and N2O. H2 and N2O. Our next task is to find the intermediates of the overall reaction. Remember, the intermediates are things that are present in the elementary step but not present in the overall reaction. So we're going to go back to our elementary steps, which are right here, and our overall reaction, which is right here. And what we're going to do is go through everything in these elementary steps and check to see if we can find them in the overall reaction. So we have H2, which is in the overall reaction. We have NO in the overall reaction. Oh, you know what I didn't do? I didn't simplify this overall reaction. I forgot to do that step when I first wrote it. We should always do that, and I did not. So let's cross off the things that we can simplify. The N2O. Okay, back to this again. H2, which we can find. NO, which we can also find. N2O, which we simplified. We removed that from the overall reaction, which means we can't find it because it's gone. So that is our intermediate. We have at least one, N2O. And let's keep going because sometimes there's more than one. H2O, which we have. H2, which we have. N2O, which we don't have, but we've already written that one down. N2 and H2O again. So we have one intermediate, and the one intermediate is N2O. Last but not least, we're going to write an overall rate law for the reaction. The overall rate law is the one that corresponds to the slow step. So to do this, we have to go back and figure out which step is slow. Slow step is going to be step number 2. Here is our individual rate law for step number 2. And we want to write this as, because we're doing this for the overall step, so we want to write rate. And we are going to say rate equals K. We're going to keep the 2 on there. H2 N2O. Now we've got a problem that our overall rate law contains an intermediate right here. And remember, that's not allowed because we cannot make any measurements on intermediates. They are not products that we're putting in. They're not reactants that we are producing. We have no way of monitoring N2O. So we're going to have to fix this. What we have to do is come up with a different expression for N2O that we can substitute into this rate law right here. So here's how we're going to do that. We're going to go to step 1, which is in equilibrium. We wrote 2 elementary steps, or we wrote 2 rate laws for step number 1, one for the forward reaction, one for the backward reaction. The definition of equilibrium is when the forward and the backward reactions are moving at the same rate. They have equal rates. This is something that you learned when we covered equilibrium. It was a really long time ago, so you may have forgotten it. But again, the definition of equilibrium is when the rate of the forward reaction is equal to the rate of the backwards reaction. And because of that, that's going to allow us to take these 2 equations right here. I'm going to copy both of them, and we're going to do some pretty cool math on these 2 equations. So by definition, because this is in equilibrium, this rate is equal to this rate, which means that this term is equal to this term right here. And we're going to start by just using that equality to combine these 2 rate laws. And then what we're going to do is rearrange this combined term to isolate our intermediate, which is N2O. We want to isolate that. We're going to do that by dividing both sides by K sub -1 and H2O. And that's going to cancel these terms out on this side. And this gives us an expression for N2O, our intermediate, which we're going to be able to stick right into that overall rate law. So we're going to use this expression for the intermediate right here and plug it into the overall rate law right here. So this is going to get really bulky. Our overall rate law is going to be rate equals K2 H2, and then instead of writing N2O, we're going to write K1 H2 NO, which is squared, over K minus 1 H2O. All of that right there. And then we're just going to simplify this to make this a little bit prettier. I'm going to simplify this by collecting all of the K's. So I'm going to have my K2, my K1, and my K to the -1. So I've just taken all of these and put all of these together. And then I'm also going to combine all of my concentrations. I've got H2, and I have another H2 as well. So that's going to be squared. And then I have the NO, which is squared. And that's going to be over the H2O. And then one thing that we'll do, that chemists will do with this overall rate law is instead of having a lot of K's in the overall rate law, they will just say K to indicate all of those. We'll say rate equals K H2 squared NO squared over H2O. And then somewhere down here we'll say, and oh, by the way, this K is being used to indicate K2, K1 over K -1. So just to kind of avoid having a whole lot of K's in here, we'll just say K, and then kind of off on the side, that's where we'll actually define exactly what K is in terms of the individual rate laws.